So now that we've seen Taylor polynomials, we can go even further to Taylor series. A Taylor series for a function at a value a is the limit of the degree n Taylor polynomial as the degree gets bigger and bigger and bigger. So just to remind you, this is right here, this is the degree n Taylor polynomial. So I'm taking the limit as the degree gets bigger and bigger and bigger. Abbreviated notation for the limit of a sum is putting an infinity symbol right here. So if I put an infinity symbol right here, that's abbreviation for the limit as n goes to infinity of the finite sum. So let's see an example of a Taylor series. So let's find the Taylor series. For the function f of x, let's do 1 minus x to the negative 1 power at x equals 0. So I'm going to write this thing down, see if I can make any sense of it. I need to take a bunch of derivatives, so let me do that. There's the 0th derivative. I could take the first derivative. The first derivative would be minus 1 times 1 minus x to the minus 2. And then using the chain rule, I get an extra minus 1. The second derivative is negative 1 times negative 2. 1 minus x to the negative 3, and then I get another negative sign from the chain rule. The third derivative, I'm starting to see a pattern. I'm going to get a negative 3 in front. That's going to give me negative 1, negative 2 times negative 3. And then I'm going to get 3 negative signs over here. When you simplify all that, I believe you get 3 factorial 1 minus x to the negative 4. Then when you take the fourth derivative, you're going to get an extra 4 in front, giving me 4 factorial. In general, if I take k derivatives, I will find k factorial 1 minus x to the negative k plus 1. So that means if I plug in 0, my a value, I get k factorial. So plugging in x equals 0 gives me 1 to some power times k factorial. So the Taylor series for this function, which you could write as 1 over 1 minus x, is the sum, k going from 0 to infinity, of k factorial divided by an extra k factorial, x minus 0 to the k. So this is the sum, k going from 0 on, of x to the k power, which if you'd like is the same as 1 plus x to the first plus x squared plus x to the third, and never stopping. So that's the Taylor series, but this gives a question. When does this thing even make any sense? So this is the main question. Main question. For which values of x does this even make sense? Does, the infinite sum make sense? when is it equal to this function? What I'm saying is, some values of x give complete nonsense here. Give infinity, for example. If I plug in x equals 1, here, I get 1 plus 1 plus 1 plus 1 forever. That's infinity. That's not really a sensible answer for me. I want to know what values of x can I plug in here to actually get a finite number out, and which values of x can I plug in to make this equation actually true. The idea is, the larger n is in my Taylor polynomial, the better of an approximation I get to my function. But what if I take the limit as the degree gets larger and larger and larger? Do I ever actually get my function? Sometimes you will, and sometimes you won't. So here is an algebra fact that'll help me answer this question. So here's an algebra fact. Algebra fact. So the algebra fact I want to use here is 1 plus x squared until I get up to x to the n times 1 minus x can be simplified. So if I multiply this out, you could do a big distributive property, a big giant FOIL, I guess, multiplying everything in this first parentheses by 1 gives me 1 plus x squared up to x to the n. If I multiply everything in this parentheses by negative x, I get negative x squared, negative x to the third, till I get to negative x to the n, negative x to the n plus 1. All of these terms will cancel with all of these terms, and I will just be left with 1 minus x to the n plus 1. So therefore, I could take this equation and divide both sides by 1 minus x, and I find 1 plus x squared up to x to the n is 1 minus x to the n plus 1 over 1 minus x. Okay, so I'm going to move that up here so I could work a little bit more. Now, therefore, this says that if I take the limit as n goes to infinity of this thing, that's the same as the limit as n goes to infinity of 1 minus x to the n plus 1 over 1 minus x. Now the only thing that involves n here is this x to the n plus 1 power. If n gets bigger and bigger, I'm taking x to bigger and bigger powers. If x is a number bigger than 1, like say, for example, x is 5, 5 to bigger and bigger powers gets bigger and bigger. I don't really want that to happen. I want to figure out when this is actually a finite number. Well, if you think about it for a minute, you might see that if x is in between negative 1 and 1, then powers of x get smaller. So 1/2 squared is smaller than 1/2. 1/2 cubed is smaller than 1/2 squared. So if x is in between negative 1 and 1, and you raise x to a power, things get smaller. In that case, this term will have limit 0. So if x is in between negative 1 and 1, this power of x to the n plus 1 term goes away in the limit. The limit of that term is 0, and I get 1 over 1 minus x. If this power here is, if x is bigger than 1 or less than negative 1, these terms won't go to 0. They'll get bigger and bigger or flip-flop between negative and positive terms. I'm just going to put this as nonsense if not. So we've reached somewhat of a conclusion. Let me write this down because this is kind of a nice result. So here's conclusion. 1 over 1 minus x is equal to the infinite sum 1 plus x squared. That goes on forever. If you'd want, you could write it as the sum k going from 0 to infinity of x to the k power. This is true when x is in between negative 1 and 1. This result's actually kind of important. The name for this series, the name for this result is a geometric series. Okay, so in this video, I did two main things. The first thing is I defined Taylor's series. So let me go back and show you what the Taylor series was. The Taylor series is the limit as n goes to infinity of your Taylor polynomial. That's the main definition. And then we did an example. We found the Taylor series for the function 1 over 1 minus x. Some values of x make this equation true. Some values of x don't make it true. And we found the values of x that make this equation true are those values in between negative 1 and 1. This series has a name, the geometric series. We'll see some more examples of geometric series in our next video. All right, I'll see you then.